Okay, well and good. So this is the video lecture, online video lecture on data structures. We are discussing about module 4. So module 4 is nothing but a trees. Trees is a non-linear data structure. So in the previous classes, we have gone with terminologies so of the tree. Next we seen what is binary tree and types of binary tree and also some properties. So which are the types of binary tree we have seen? It is a complete or fully binary tree, almost complete binary tree, and strictly binary tree. So binary tree is one topic. Inside that we are having three types. So that is fully or complete. Second one is almost complete. Third one is strictly binary tree. So in today's class we will see the remaining two topics of our first class. So which are the two we have till now we have seen types and properties. So in today's class we will be seeing again properties and array representation. So properties and array representation will be seen in today's class. So come for the properties. So we have already seen in a binary tree will be having minimum of 0 or 2 children. So if there are no children also, we consider that one as binary tree. And if it is having children, so then how many children it can have? It can have 2 children. So that's why we can tell that number of leaf nodes is always one more than nodes with 2 children. So nodes with 2 children, we can call it as internal node. So nodes with 2 children means it is nothing but other than leaf node. Whatever you are having, they are called as say internal nodes. So keep in your mind, root node is also can be represented as internal node because from the root node you will be having 2 children. So okay, so that means so leaf node is equal to internal node plus 1. So you can represent like leaf L is the leaf node is equal to internal node plus 1. So if the number of internal nodes are 3, leaf nodes will be 4. Okay, so similarly, now you come for the second one, the maximum number of nodes at level I. What how you represent the level? So a level will be given from root will consist of level 0. In next children of root will be considered at level 1 and children of internal node will be considered as level 2. So that will be the that is the concept here. So levels will be in 0 1 2. So 0 you will be having 0 you will be having root node. If it is only 3, okay, so root node will be at level 0, internal node will be at level 1 and all the leaf nodes will be at level 2. Okay, so maximum number of nodes at the level L, so it is given as 2 power L. Okay, so you keep in your mind, so it is number of leaf you take it. So maximum number of leaf nodes at level L is 2 power L. Okay, so next you come for the next one, come for the height concept. Maximum number of nodes of height h is 2 power h plus 1 minus 1. So maximum number of leaf nodes at level L is 2 power L. Maximum number of nodes in the binary tree of height h is 2 power h plus 1 minus 1. Okay, so similarly you have gone with the maximum level and height. Now you come for the minimum level and height. Okay, so in a binary tree with n nodes, minimum possible height or minimum number of levels. So minimum you should be having log n plus 1 to base L, n plus L. Okay, so maximum n log of n plus 1 to base 2. Similarly, a binary tree with L leaves has at least log n plus 1 levels. Okay, so this is binary tree with n nodes. We have minimum possible height or minimum number of levels is given as log n plus 1 to base 2. So similarly, a binary tree with L leaves will have log L plus 1 levels. So these are the properties of the binary tree. Okay. So after the properties, now you come for the next topic. So next topic you see, it is the very important concept. So it is representation of the binary tree. So how you represent a binary tree? So talking about the representation, the trees can be represented in two ways. So how you represent the tree? One using linked list representation and the other one is using array representation. Okay. So one is linked list representation, the other one is array, that is sequential. So that's why we tell it as, so that's why we tell this one as dynamic node representation. For which one? Linked list. And next you have array representation, that is so array representation, we call it as sequential representation. Okay. So how the linked list and array are going to represent, now we shall see with the diagram. Okay. So we, in this particular slide, we are going to talk about sequential representation. So sequential means it is array representation. So if it is linked representation means it is dynamic node representation using linked list. Okay, for now, we are discussing about array representation. Okay, so to represent the tree using an array, the numbering of nodes can either start from 0 to n minus 1 or 1 to n. So actually, the representing, it will be, so representing it will be started from 0 only because root node will be starts at 0. So no node will start at 1. So defaultly it will be starting at 0 to n minus 1. Okay. So children of nth node will be at 2nth and 2nth plus 1 position. So children of the nth node will be at 2nth and 2nth plus 1 position. So similarly, parent of nth node will be at int of n by 2th position. So keep this one in your mind. Where are the children and parent? So children will be at 2n and 2n plus 1th position. That is left child will be at 2nth and right child will be at 2nth plus 1 position. Whereas parent, if you want the parent of nth node, it will be at n by 2th position. Okay. So here you see this is the so representation of array. So this is the tree we have considered. So for this tree, the array representation, you start from here. A will be represented of 0 because A is the root node. Okay. So A is at root node. Can you tell which type of tree it is? So this is the binary tree. Which type of tree it is? Can you tell? So which type of tree it is? So I'm almost complete. Uh, Whether it is complete or it is almost complete or it is strict. So you should tell me. So we have three types of trees. One is the complete, second almost complete, third strict. So what is the condition for complete? Kindly replay. GK Bhargava, are you there? Two childs. So keep this one in your mind. So when you tell it as complete, so you can go and check there. Okay. So when we call it as complete, so see here. So I have marked here. All internal nodes have two children. Okay, all the internal nodes have two children and all leaf nodes are at same level. At that time only we call full binary tree. So after that, now you come for this one. So almost complete binary tree means each level is having two children, but at the last level, they or may not be filled. So at level 0, you have everything filled. At last level, which is the last level? Level 2. So at level 2, you may or may not fill it. So that one we call it as complete. So similarly come for the strict. All internal nodes will have 0 or 2 children. All the internal nodes will have 0 or 2 children. Now you come for this diagram. So here you see which are the leaf nodes. Can anybody can answer which are the leaf nodes in this diagram? So which are the leaf nodes here? E. So here you start checking from the first. So first condition is fully binary tree. So for fully binary tree, every node should have two children and all the leaf nodes should be at same level. Or all the leaf nodes are at same level here? So here you see A is at level 0, B and C are at level 1 and D is the leaf node at different level and F and G are at different level. So this is not fully binary tree. Okay. So after that, now you come for the next one. So next one is almost complete binary tree. So almost complete binary tree, what it tells? So at the last level, there may or may not be at the last level, which is the last level you are having. So last level is level 0, level 1, level 2, level 3. So at level 3, there is no nodes. So here also you are having no nodes. So this represent it is almost a complete binary tree. So come for the strict binary tree. So strict means all the internal nodes. Which are the internal nodes here? Can anybody can tell? So internal nodes. So which are the internal nodes here? Internal nodes is C, B and E. Okay. If C, B and E should not have, we should have either 0 children or 2 children. Is it satisfying? So internal nodes are B, C and E. So should have 0 children or 2 children. But you see B is having 1 children, C is having 1 children and E is having 2 children. So is it strictly binary tree? So it is not strictly binary tree because in strictly binary tree, all the internal nodes should have degree 0 or degree 2. but B is having degree 1. That is, B is containing one node, C is containing one node, and E is containing two nodes. So for this purpose, we can't tell it is strictly binary tree, but you can tell it is almost a complete binary tree. So what is the meaning of complete binary tree? So complete binary tree means the last level may or may not contain the values. So B also, which is the last level. So if it is B contains some values, then we can tell it as, so this is a almost complete binary tree. Okay, understanding? Are you people understanding? Okay, now you see A is at level 0, B1, C2, next D3, E4 and F is 6. So how you tell F is 6? So 0, 1, 2, 3, 4, and this should be 5 and this should be 6. Okay, so that is the one representation you can take, or you can take like this also. So you can start with A is equal to 1. So here I have started with 0, but here I am starting with 1. A1, B2, C3, D4, E5, F is at 6, and G is at 7. So always you should move from root, next comes left, next comes right. So this is the representation what you can take in array. So as you all know, array is a group of elements of same data type. It is a structured data structure. Okay, so first comes A, next comes B and C, next comes D. So here you see, so after B you should have left as well as right, but B is containing B. After B, C, go for B. So it is containing D, but there is no location at 5. Okay, so that's why we take it as empty. So you can see here at 5th location it is empty. Understood? So after that, now you come for the C part. E is at 6th, and you see this one is at empty. So which is empty? E. After E, C right part is empty. So after C right part, next you can go with F and G. So that will be the locations of array representation. Okay, so now you come for the next one, linked list representation. The same thing, how you are representing that one in the linked list, that we shall see. So which are the fields of the linked list we have? So we have linked list, we will be having two pointers now. So it is the doubly linked list. On left you have one pointer, on right you have one pointer. So left, there you are considering the left pointer as previous and right pointer as next. But here you should see the left pointer we call it as left child and right pointer we call it as right child. So binaries and linked list are stored in the memory as linked list. These lists have nodes that aren't stored at the neighboring memory location, and they are linked to each other through the parent-child relationship. Okay, so if they ask you the linked representation of the binary tree, then you have to write like this. So first you will get the data part, next you will be getting star left and star right. So star left we will go with a left child or left subtree, and star right will go with the right child or right subtree. So now you see here, this is the linked representation for the binary tree. So first you start with A. So on A left part you will be having B, on A right part you have C. So on A left part you see this is the left. B is containing, B is there, so that's why B is represented here. Here C is there, C is represented here. Okay, so B After B, is B is connected to anything? So B left you are having D, on B right there is nothing. That means, so you can see here on B right part you are not having anything. So that's why here we mark it into. Into means end of the list. So what is this into will mark? It will mark the end of the list. So similarly, A then C. C part is there. From C, left part you have E. On right part there is nothing. On left part you have put E. On right part you have put a null. So this into mark will represent again there is no right subtree. Okay. So now you come for the E part. So E is having both left as well as right. So that's why we represent it as F and this one as G. Here you see the right part. Here it is no right part. Here also no right part. But here you are having two. So from E you are getting F and G. So this is the binary linked representation of the binary tree. So have you understood this array and linked representation? Any doubts in this? Any doubts you have? So use this attendance link to answer your attendance. So now you come for some of the review questions under that. So maximum number of nodes in a perfect binary tree at level. So what can be the, so at level L is equal to how much? So what is the maximum number of nodes at level L? In perfect binary tree. So I will tell you maximum number of leaf nodes you take it. Maximum number of leaf nodes at level L. What can be the answer for that? Anybody can answer. Maximum number of leaf nodes in complete binary tree at level L. So it is 2 to the power L. So it is 2 power L. Okay. So a maximum number of nodes in perfect binary tree and strictly binary tree that you have to go with the properties. Okay. So in array representation of the binary tree, where will be the children of the nth node? So for that you see the children of the nth node will be at, left child will be at 2nth position and right child will be at 2n plus 1 position. Understood? So this is the some of the important questions, and these are the references we have gone through for understanding this particular concepts. So this is up to trees with its binary tree properties and array representation. So I hope you all got understood this particular concept. So we shall see the remaining next coming topics in the next week. Okay. So this video lecture will be subscribed. This video lecture will be uploaded in YouTube. You can go through and understand. Kindly like, share, and subscribe for my channel. Okay. Thank you, one and all.